About designing with layers and composition and an aim towards testability. Quick side note, you may have seen some announcements that Study Abroad, just about in every program, extended the applications for all programs that I'm aware of, and the new deadline is this coming Sunday. So there's still plenty of time to do this. The application's not intense. We'll be running a great program in Copenhagen late May, early June, with typically enough time to do an internship afterwards. If you have any questions about it, feel free to email me, or let's talk about it after class. Cool. So what are we looking at today? We're going to look at layers in a system. We're going to talk a bit about composition, and then some strategies for isolation. But the warm-up here is I would like you on a whiteboard at your table, so you won't need your computers today. You can put those away. You only need maybe something to take notes on. You can do one whiteboard per table. That's fine. Can you find a few things wrong with this house concept? Let's spend 2 or 3 minutes on this. 1, 2, 3, go. Try and be specific. Thirty more seconds on this. 30 more seconds. All right. I might go to Zone C. You all have anything at this table? What do you got for me?
The base is fully exposed.
The base is fully exposed. You got a very open foundation there. That's a problem. What do you all have besides foundation?
We said that that diagonal support beam is exposed on the outside.
That diagonal support beam is a little questionable. I would agree with that. What do you all have? Bottom pillar standing on a rock. Yeah, that's dubious, right? And not only that, but at that stage, where you would expect to be foundation layer, you see a pillar that shouldn't be structural. You may have noticed it also looks like there's a structural plumbing pipe here. That's dubious. You don't want to generally build a house where your plumbing is supporting something of the structure itself. There's a ton wrong with this, right? And what I want to try and convince you of is that there's a lot of layering that's being abused here. There's violations of layering here, right? There's things that are a part of what should be the foundation that aren't the foundation. They're lacking walls. We're lacking finish along some of these boards. And so the general layers of a house where you've got a nice foundation, you've got coherent framing, you've got a nice roof on top of that. There's some violations of proper layering that would create real problems if someone were crazy enough to try and build something like this. what I also want to posit to you is that you will in your lifetime, and you may have already, encounter a code base that feels like this, where there's like things happening in the front end that should be in the back end, or you're handling something in one layer that really was not supposed to be there. And so what we're talking about today, and I wanted to motivate that with an analogy of a house, is that in software engineering, a very common strategy for building robust systems is using a layered architecture. And this is a design style where each layer, and I apologize for this flickering. Let me see if there's just a connection here. Yikes, 1 second. Where each layer depends and rests upon what comes beneath it, right? I'm going to try this again. There we go, cool. So if we look at this is effectively all the primary layers of a pretty modern full 3-tier web application. The first tier is the client, so those are the first 3 layers. You've got a user interface, some front-end services running on your web browser. Another, you could call it a layer of the system. There's a networking layer to this component. What's interesting about networking is if you go and you take a class COMP423 is you'll learn that the whole internet, its architecture is built in a layered way, in a very intentional, it's one of the most classic examples of a layered system and its benefits. So there's more layers in there. And then in the back end, on the server side, a web server, some API router, some back-end services, and something to store your data. And typically what's true in these layered systems is a request will come in from one layer towards the top and work its way down, such that layers don't really know about and don't care about what sits on top of them, right? So you think of the foundation of a house, it's built before it has any idea of what's going to be resting on top of it, but it's supporting everything that's on top of it. Similarly, in this architecture, it would be really strange to have a data persistence layer that's very aware of something going on in the user interface. And that would create some complexities and some code mess if that were true. So when we build and design software in layers, we tend to assume that we're going to rest one layer upon another and implement it in terms of the layer most directly beneath it. There might be some cases where you would reach a layer or two beneath you, but typically it's a best practice, and it leads to the cleanest code bases to only depend on what comes directly beneath you in some slightly lower layer. And then beyond that, it's going to be doing something similar until it reaches the bottom layer of the stack. Similarly, once a result of some action is ready to be returned, those values tend to bubble back up. Oftentimes it'll be translated, so what success looks like when you save an object in a database at the very bottom layer will be translated a few times until at the web server it might actually report back to a client saying, hey, your transaction succeeded and your balance is so-and-so. The data persistence layer would just say, okay, this save succeeded, and it wouldn't necessarily know more about the semantics of what the problem being solved was. Similarly, your web server would know nothing about what label to show in the user interface when it comes time to send a message to the user saying, here's what we want to display when they look at the result of this action that they just took. Like you just double-clicked on a photo on Instagram, you would see that request to like a photo goes all the way down. It comes all the way back up, and finally at the user interface level, you've drawn in some pixels on your heart to know that you liked some photo. So this is the type of architecture that we'll see throughout a course like the one we're in. We've actually already looked at a similar architecture in artificial intelligence, where we had the chatbot and an agent built on top of chat, which is pretty interesting. And I want to ask, beyond what I just gave at a very high level, can you come up with 3 motivations as a table? And this will wind up being today's, and you can actually come up with more than 3. This will be today's activity for attendance. So beyond some of what I just described in terms of how layers work, what are the benefits, or why would you go to this effort of adding these layers? And try and think, what upsides might it have? for a project and a team that's working on a large software system. And let's spend 3 minutes on this trying to brainstorm why go to the trouble to have a layered system. And you can also think about some analogies with the house as motivation for this. "30 more seconds on this. Once you have it, take your team selfie and have one of you upload it to Gradescope for today's attendance." Oh, no wonder. One more minute on this. One more minute. 30 more seconds, 30 more seconds. All right, I'm gonna come back to, let's try F and see if we can get some inspiration in zone F. Anyone feel very positively about, I love your first one. What's your first one? Parts are separated for debugging. Yeah, so when you have a separation of concerns, you can isolate where in the system some particular bug might be coming from. And we'll be looking at ways of using our understanding of this layered system to trace where a bug might be in our code. And oftentimes we wind up applying a binary search where we look and see, did our request even make it down to the server? And if it didn't, we know it's in the client. Or if it did, and it looks like it succeeded on the server, then we also would know it's in the client. But if we see something weird coming back from the server or nothing at all, we would know that we would need to look there. And it can actually speed up our ability to debug a system. Let's see. Helps with organization is the top of this one. And yes, so I saw this in a few places where when you are trying to organize a code base and scale out a code base, you can imagine if I used Instagram as an example, there are entire teams of people at Meta who are working on individual tiers, right? In fact, I bet at the data tier, there's hundreds of people working on the lowest levels of the stack. And so by separating concerns, you can assign people who specialize and focus on just this layer of the stack. And you're able to do so thanks to knowing you don't really have to worry. If you're working on an API router, you really don't have to worry much about what's going on in the front end or things like that, as long as you're putting forth a contract saying, here's what our capability is going to be. And you know that there's things that you can depend on beneath you in the back-end services, like here's the contract for back-end services. Their team is going to make sure that they provide these certain methods to you or APIs to you. And your job is just to focus entirely on the implementation of that one layer. It allows you to be a little bit more efficient in how you work, and it allows you to scale out a team to be focused on a specific part of the stack. There are a few. So this was one of what we just talked about. Each layer has one kind of responsibility. This relates to a classic object-oriented principle where a class should have one driving purpose in modeling something. Similarly, a layer tends to have one driving purpose in what its job is, and it's going to delegate to some other layer something that it depends upon. Right? So your API route layer really shouldn't need to know the details or how the sausage is made and saving data to a disk. That's the disk layer or the storage layer's job. Clear interfaces and contracts between layers. This is how we reduce coupling between two layers. And so you all learned quite a bit about interfaces in 301 in the Java context or in the object-oriented sense. And that winds up being super important for layers of an architecture. So each layer effectively has its own interfaces and contracts that it's promising to something above it, and then each layer that depends on something beneath it, as we just discussed, is going to know what it can expect from the layer right beneath it. The dependency direction is typically always down, so you don't have circular dependencies, which can create real problems. You don't have the back-end code depending on front-end code or things like that. And so this winds up having helpful properties in implementation. Another thing that we're going to see that's very nice is you can actually swap out implementations of certain layers. And we'll see that this winds up being valuable for testing purposes and is important for us being able to test without having the whole thing, without having most tests be integration or end-to-end tests. And I saw this on a few whiteboards as well. Maintainability is important. So it gives you localized changes. I saw someone who, I think one of the tables over here, had onboarding becomes easier. Yeah, like as soon as you get to a large company, if you're on a team that's responsible for the front-end application, you can focus at just those layers of the stack and not really have to know what's going on the back end. In fact, I had lunch with an alumni who's at Meta who's working on the comments feature of Instagram. And I asked him, like, how much do you know about the data layer of what's going on and how your comments are stored? And he had no clue what was happening to actually store where the comments would be stored on disk at the end of the day. And you can get away with that at a very large company like Meta, but we're going to try and gain familiarity throughout the entirety of the stack today. And then testability is very important as well. And this ties in with replaceability and some features there. But if you're very intentional about how you layer a system, you can test each layer of the system very well. And in doing so, you can effectively guarantee the contracts of the interfaces that connect between the layers of the system. Any questions on the concepts at play here, some of the dynamics of the forces of layering in an architecture? Cool. So the guiding question that's going to sort of segue into where we're going next is, how do you test layers other than the base layer? Like, you can kind of imagine the base layer is pretty straightforward. There's nothing that it's depending on it. But how do you actually test individual layers outside of it? And so in order to motivate this, I want to briefly talk through just a little bit of Python code to set up some examples. And I'm going to switch back over to my iPad really quickly to highlight a few things. My pencil might be dead. So I will talk through this. For those of you who haven't seen Python in a while, remember init is your constructor. One of the things that we do in 110 that's not necessarily a true Pythonism is we will declare our instance variables or the properties of an object above our constructor. But in Python, thanks to it being a dynamic language, it's actually pretty conventional to just initialize whatever the attributes or properties or instance variables, whatever you want to call them. In this case, the balances attribute of this class is just a dictionary or a hash map from key type string to some integer, because this is a silly trivial example. That's the balances of Alice and Bob's accounts, and that's how this is getting initialized. And you can imagine that this account storage has two facilities. You can get a balance back, and you can set the balance to something new, right? So this is and I should note that there's no data persistence happening here. We're just trying to make a very trivial example. If there were persistence happening, there'd be some mechanism for saving this to a database or to files on our hard drive. This is just it happening in memory for sample's sake, all right? So what would a backend service look like? Well, here, we're going to continue on with this withdrawal example. So notice when we construct an account service, we're giving it a store, so an account store. It's storing that as an instance variable. And then the withdrawal method has a little bit of logic to it, right? Pretty straightforward. If you don't have any money, or if you're asking to withdraw a negative amount, it must be positive. We're checking the balance to be sure that there's enough in the balance. And we're setting a new balance if there is, and returning the new balance. Not super important. This is, again, just meant to be a sort of a toy example. But this is what a service layer might look like. And then we're about to look at APIs. So you're going to see some things on this slide that we don't have full context for. But in order to expose some functionality out to the internet or to a web application, we we'll write some functions that have special decoration to them. So the app.post, that's this, it looks like an annotation, or in Python, these are called decorators. And they're related to the decorators you learned about in 301. They're a little bit different, but very similar in spirit, that this is going to wrap some functionality around this withdrawal function. And basically what we're saying is we're giving the internet a way to send data to this particular function through our API. And so this is what an API router function looks like. And we're expecting as inputs the account ID and some amount. And then we're going to learn a little bit about dependency injection. It will relate very closely to what we're talking about today. But there's some cool things that happen to get that third parameter service, which is an account service instance, what we just looked at, right? And so the implementation here is we try and get the new balance. We'll return that. Otherwise, if there's some kind of exception in our service, we raise an HTTP exception, a 400 error You all might have seen 404 errors, like a page not found. This is some other generic client error, or sorry, generic server error saying, hey, the thing that you tried to do, we couldn't actually succeed at. We tried, and an error occurred, and that would be the exception handling case. And I want to point out that there's 3 different levels of concern here, right? So at the very first level of concern, it's just some basic state maintenance in our data. At the services level, this is where our business logic, quote unquote, would be. And that's sort of determining, hey, can we actually withdraw some money from it? And then at the API router layer, this has our concern with the web, right? And here we are aware of status error codes, we're aware of URLs and things like that. We have some awareness of the web, but we're pretty quickly going to delegate the actual logic to our service layer where the business logic is, and it's ultimately going to use some layer below it for persistence. Questions on the setup for this example? Right, so what I'd like you all to do is actually, let me switch over to my slide deck for a second. 30 seconds to discuss the question on the slide. Suppose the white dotted layers are not subject to a given test. Which of these would be a unit test and which is an integration test? And actually, I'll go ahead and kick it off to you all. How would you isolate the layers in A? Like if you needed to write a test, how do you think you would set up A to test it? And you can sort of wave your hands and just describe this at a high level. That one's pretty straightforward. But how would you set up B in order to test it and isolate the backend services from the data persistence layer below it? And you don't need a specific solution to this. You're not writing code or anything. But I want you to try and think to which object-oriented ideas would make it possible to isolate one object from other objects that it might otherwise be connected to. So let's spend 1 minute discussing what comes to mind, thinking about this at a high level, and then we'll come back and talk through it as a class. Let me see if it'll. Thirty more seconds. Anyone have some key buzzwords from COMP423 that came to mind here and might be at play? I'll ask for volunteers in section C. Were there any ideas from 301? Yep. Abstraction. Tell me a little bit more.
Like it's much easier to swap swap something out if there's, like you're talking about interfaces, so it doesn't have to know the actual interworkings of something else?
Yes, so we have an abstraction for the data persistence layer, and we can swap something in and out. That's exactly the right intuition. There's another word from 301 that describes the swapping out ability. Does anyone remember that? Yep. Dependency injection. Is that what? Yes. That's one way of doing this, but what is dependency injection exploiting, or what is it bringing together? Yep. Yes, composition. Sorry, what was the last part you said? Yeah, composition over inheritance, yes. And so these three things come together. There's abstraction at play that allows us to compose these objects. And what we'll see is in modern frameworks, we use dependency injection for this composition, right? But composition is the big idea and abstraction that are going to allow us to say, you know what, we're going to swap out this whole layer of data persistence with something that's not quite as real and be able to test it. And that's thanks to our ability to abstract the details of that away to an interface. And so, of course, I hope it was pretty straightforward to imagine that the A example here would be an integration test. And how would you actually set this up? Well, it would look just like using backend services directly. You wouldn't have to do anything super special to set this up, because if you're using backend services in the same way that the API router is, it's going to probably by default be depending on the standard data persistence layer. It takes a little bit more intention to isolate a unit test, which is what B is representing, and we're going to have to do this. We're going to have to do something clever to swap out the data persistence layer. So composition is at play, and I don't think this one's worth discussion. I think it's hopefully pretty straightforward. That if you look at these two examples below, one of them is more flexible than the other, right? So in the first example, we see that we're initializing an instance variable named store to a new account store instance. And in the second option, we're setting up as our constructor the ability to pass a reference in. You might say to inject behavior or an instance of something that has the interface of an account store and use that to initialize our store instance variable here, right? And so this second option is going to, it is more flexible. And this is the difference between tightly coupled composition. This is still an example of composition on the left, right? So our service would be composed with the account store, but it's very tightly coupled. We've just constructed it, and I think you all learned, and it was beaten into your heads enough in 301 that this is generally not a best practice, right? Like where possible, you want to be able to compose with flexibility, or looser coupling is what we tend to call it, right? So in a loosely coupled composition or an injection-based composition, we see the ability to provide as an argument to a constructor or a function call what it is composing with, right? So any object, and this gets back to the notion of abstraction, this is where abstraction is important, any object that implements the account store interface or a subclass of it, or in Python we can use just any object that actually has the same methods defined on it, we could pass as an argument to a new service construction, and we've effectively swapped out that whole layer of the stack in order to make it more testable. So my question to you all, and I kind of gave this away, but I do want you all to talk about this. So this is a little bit small on the screen, but nothing's changed from before. What strategy would you use to isolate the account service from the account store in order to write a test for account service, right? So how could you test account service without actually depending on or testing the implementation of account store? And I want you to talk about a strategy that you could use in order to do that. And maybe write some pseudocode for this if you're feeling confident. 1, 2, 3, go and discuss. 30 more seconds, 30 more seconds. Five more seconds. So I heard some of you using the word mock, and we'll talk about mocking in just a moment. But I was hoping that we might derive as a more immediate extension of what you learned in 301 is actually a simpler way of doing it than, well, I shouldn't say it's a simpler way. It's a more direct way without having to know anything other than what you learned in 301 in order to achieve this, which would be to extend the account store class with a fake account store. And so you can imagine writing a class in your test file that is a fake negative balance account store. And in Python, we say that we inherit from, or this is a subclass of account store by parameterizing in that way. And then, this is a totally fake account store. All we're going to do is just hard code return negative 100 from it there, and then we're just going to pass or do nothing with set balance, right? And we could make use of that by first constructing that instance, and then we can go and construct our account service. We didn't have to change anything about account service, right? That's still all the same. But because of composition, because of this abstraction of an account store that this subclass actually implements, we can pass this fake account store to our service and test by isolating just the layer of this service, right? We actually have full control now of not depending on what came beneath it, because we're overriding it with something very simple that we have full control over. And here we can assert that, that PyTest, this is the way of checking to be sure that a test raised an exception or raised an error. And that would confirm in this test that, yes, that our service behaved in the way that it would. But the key idea here is, thanks to our loose coupling and our ability to compose objects when we construct them, we're able to control what's subject to our test, right? And so this gives us the ability to just pick one layer or one specific class, this is a single unit, and isolate it from the dependencies that come beneath it, right? Any questions on this idea? And so this is thanks to subclassing, right? Some of you had talked about mocking, and yes, mocking is another way of doing this. But before we talk about mocking, I'm actually very curious where our level of understanding is at in this course about the differences between a static language that's compiled, like Java, and a dynamic language that's interpreted, like Python or JavaScript. And what I'd like you to try doing is list 3 things that you can do in Python that you can't do in Java on your whiteboards, and spend 2 minutes on this. 1, 2, 3, go. 30 more seconds. All right, so walking around, I noticed that everyone seemed pretty comfortable, or most tables seem pretty comfortable with the notion that you don't really have to specify a variable's type in Python, you do in Java. And that is a big difference. I saw a few folks that recognized if you define a variable and give it a type, it doesn't actually matter. You can assign whatever you want to it. It can be any other type, and your program will still run. It's just questionable about what will happen when it does run. And what I'm realizing is we should probably have a full lecture on some of the key differences between a dynamic interpreted language and a statically compiled language, because there are some very fundamental differences. And we do everything we can to hide those differences from you in a class like COMP423 because, honestly, you're just too young. It's like there are things you shouldn't know about at a certain age, and what I'm about to show you, you shouldn't know about in 110. Like, we don't want you to know it in that class. And there are like motivations for me to want you to not to know it in this class. However, to use mocking appropriately, you kind of need to know how the heck does it pull this off, because it feels like magic otherwise. So I want to share with you a few things that I want you to know that are bad practices in Python, but nothing actually stops you from doing this. And I hope that you feel somewhat appalled in seeing these things. I mean, this is almost, content warning. Explicit code is about to be shown. The first, you can declare a class that has nothing as a part of it. You can instantiate that class, and you can assign attributes to it, whatever you want, right? So we just added a favorite field or attribute to this instance of empty. We could make another instance of empty, and it wouldn't have a favorite attribute, right? You can do this with any type of object in Python. And this is one of the features of a dynamic interpreted language. This is true in JavaScript as well. And this wouldn't compile in Java, right? So you can invent new attributes for objects right on the fly. And what we're about to see with magic mocking, it actually uses this for good, not evil. Another example, you can import the math library. You can override the square root function of the math library to return the string LOL nope, such that if later in this module, specifically in this module, you called math.squareroot 9, you would get the string returned LOL nope to you. Like, this is offensive, right? You shouldn't probably ever do this, and it would be very confusing to override built-in functions in this way. So this, some of you were aware of. You could have a variable x that's assigned an integer. And we could have, on that very first line, declared it to be specifically of type int, right? x:\int is 5, and that would have been fine. But there's nothing in a dynamically interpreted language, or most of them at least, the popular ones, that prevents you from reassigning a variable to be of some completely other type, right? A string, an array, a new object, whatever you want. And there's, at runtime, when this code is evaluated, it's just going to follow these instructions, and nothing's going to prevent you from doing something like this. You should never do this. This is horrible practice, but nothing stops you from doing it, right? A really key, big, exciting, and mind-blowing, and powerful superpower, it's almost a nuclear superpower in programming, is you can actually evaluate strings as code, right? There are very significant security concerns in doing something like this, so be very careful if you ever feel tempted to do this. Probably don't, or be very careful with it, especially if it's using code submitted by a user. That's the worst case scenario. I do have to mention that this is a massive security hole. If you were to evaluate user-submitted string in any way, this is where many security issues can come from. But notice we have a string, and if we were to evaluate that string as code, at that point in time, it would be evaluated as an expression, right? This is a quick preview of a few things that you can do in a dynamic interpreted language like Python or JavaScript. There are more. But I set this up because in order to understand what a mocking library does for helping us isolate one layer of our stack from another, it's exploiting some of these interesting capabilities for good in a way that will feel confusing until you understand what's going on beneath the scenes. or beneath the hood, all right? But this might be an interesting lecture to spend more time on. So I want to preview to you, and I'm actually going to switch back over to my slide here, is what does mocking look like with Magic Mock? So Magic Mock is a built-in library, right? It's a built-in class that's defined in the module unittest.mock in Python. And it's a very common package for doing what's called mocking. And what we did before was faking. So we created an instance that was like we had a class that was a fake class. Mocking, we're not going to define a new class. We're just going to set up a new instance that has some special magical powers. And you can pretty quickly see something that I hope is a little bit uncomfortable. And that's these two lines here. So notice on the first line, we're setting up a new instance of Magic Mock. So stores type would be Magic Mock. Notice we didn't implement any interface like our store interface or anything like that. This is just an instance of this class. But one of the things we can do, because it exploits this some of the dynamic properties of Python, is we're accessing an attribute that does not exist on this class, right? Store.getBalance. That's the name of the method that we're trying to actually mock here, right? And we're saying, we're using a chained property access here to say that the return value of this method, like we're actually defining the method on this instance named getBalance through some magic, through a clever trick or a clever technique, and then saying that when that method is called, we're going to return the value -1, right? So this line effectively set up a new method on the store object that will always return -1, right? And then what we're doing with that mock is we're injecting it, or we're composing the account service with this mock. So we've effectively swapped out that whole layer beneath our service with this mock that's been isolated. And now when we run that same attempt to withdraw from this account, that's going to raise the error that leads to this successfully continuing forward. If we didn't actually raise an error here, this test would fail at this point. And then we could go and we could see that we never did call a method named setBalance. So there's some other ways of checking after you've used a mock, did methods get called, and inspecting what the call patterns were if you needed to. But the key idea, we'll look at what's going on in this part later, so don't worry about that. What I wanted to sort of motivate for today is this notion that we can use either a fake, like we saw in the first example where we extended an existing class and just overrode the methods with something very simple, or we can use some interesting mocking techniques like we're seeing here and we'll spend some more time with to write a unit test that isolates one class that depends on another from its dependency. And this is a pretty powerful concept, right? So that's all we got time for today. We'll have some readings that get posted right after class on starting to look at APIs, and there's one task that's out. Good luck in the snow. I imagine we might not have class on Monday, but we will see.